Good morning, students. Today we are going to start a topic which is hybridization. Previously, if you remember, we have studied valence bond theory, where we have studied that pure atomic orbitals are going to overlap in order to form a covalent bonding. Now, when we talk about the hybridization, we'll see a little bit difference in this theory. This theory was proposed by Slater, Pauling and Slater. And what does it tell us? First of all, we'll know about hybridization, what is hybridization, and then we'll come to know that what is the difference between this concept and the valence bond theory which you have learned previous day. So, hybridization, in general, what does it mean? It means the process of mixing of something. So here, of course, there is the process of mixing of pure atomic orbitals of nearly the same energy to produce a set of entirely new orbitals of equivalent energy. They may or may not be equivalent in shape in few cases, but they must be of equivalent energy. This is what we call as hybridization. Now we shall know about the rules for hybridization. See, only the atomic orbitals of nearly the same energy belonging to the same atom can take part in the hybridization process. Those orbitals which are taking part must be almost same in energy. Varied energy orbitals will not take part with this mixing up. That is in the process of hybridization. Secondly is, most of the hybrid orbitals are similar in shape and energy. Of course, it must be similar in energy, but in few cases it may not be similar in shape. Due to the 3D orientations in space, it may not be same. The third part is that orbitals containing unpaired electrons undergoes hybridization. As we have studied this and also in valence bond theory, that pure atomic orbitals only with unpaired electrons were going in the participation with covalent bond formation. But here, unpaired electrons containing orbitals of course will go into the hybridization process, but in few cases it is seen that the paired electrons, the orbitals which contains the paired electrons, can also go for hybridization process. This is the main difference we are getting with the valence bond theory. This one and the other one is that here pure atomic orbitals are not involved in covalent bond formation. Hybrid orbitals are involved. There in the case of valence bond theory, we have seen only pure atomic orbitals going into the covalent bond formation, participating in the covalent bond formation. Okay, here this is the case with the molecules containing lone pairs. The molecules in which the central atom contains lone pairs, as in the case of NH3 or in the case of water, where the central element, that is oxygen, is carrying lone pair of electrons. In those cases, we will be seeing that even the orbitals containing the paired electrons can undergo hybridization process. Okay. Now, why does this hybridization taking place? Of course, it is for the stability purpose. Okay. So, a hybrid bond will obviously be stronger than a non-hybrid one, and thus we can understand that hybridization increases stability. So, of course, the other theories which are coming into play will tell us about more stability, of course. Okay. The fifth point is that if all the hybrid orbitals contain the shared pair of electrons only, then the molecule has a regular geometry. But if the central element is containing lone pair of electrons, then the molecule, the geometry of the molecule is distorted, as you can see in the case of H2O or in the case of NH3, where it's not the normal tetrahedron angle we have just known. Before also we have known that. Okay, so these were the rules of hybridization, and most importantly, you must have got the difference between the valence bond theory and What does the valence bond theory tells us, and what does this hybridization concept is telling us? Two main differences which I told you is that first one is, there in the case of valence bond theory, only pure atomic orbitals were involved. Here in the case of hybridization, covalent bond formation is being done by the hybrid orbitals, not the pure atomic orbitals, but the hybrid orbitals. Okay. Secondly, we have seen there that in the valence bond theory that only the orbitals which are carrying unpaired electrons was involved in the mixing up or overlapping, not mixing up, overlapping. But in the case of this hybridization, we are seeing that the molecules where the central element is carrying the lone pair of electrons, in those cases, even the orbitals containing the paired electrons can undergo the bond, mixing up and go for the covalent bond formations. Okay, so this example where you will be seeing that the molecules containing the where the central element is containing the lone pair of electrons undergoing hybridization even with the orbitals containing the paired electrons will be shown later. Okay, we'll have example for that, and I'll give you some more to do it. So let's go for the next thing, that is sp hybridization. When we talk about sp hybridization, we just start all the hybridizations from s orbitals. Okay, s orbitals are involved because in all the shells, on all the orbits, you will have s orbitals, orbitals. Okay, so here, as you can see from the name, one s and one p orbitals will be involved, and whenever it is such, almost this in the cases px orbital is involved. Okay, px. So when we draw it in this way, we write first px and then py and then pz. Okay, so it is seen that whenever these two orbitals will be mixing up with each other, again two hybrid orbitals are formed. So the number of, that was another most important point, that number of atomic orbitals which are involved in hybridization purpose, please remember this, okay, in hybridization will be equal to the number of hybrid orbitals which is formed. So if I am saying that two atomic orbitals are involved in this hybridization, so how many of the hybrid orbitals will be formed? Two. Okay. Now generally what happens, we can write the hybrid orbital shape as this way. See, a larger lobe and a smaller lobe. So here in this case, after mixing of these two pure atomic orbitals, we got two hybrid orbitals, and that is shown here. See, two sp orbitals. So this is one of them, and this is, see, this lobe here. Okay, this is one of them. Okay. So let us see the BCl2 molecule for an example for this hybridization. This is sp hybridization. Beryllium in ground state, what is its electronic configuration? Beryllium is your 1s2. 1s2 will not write it, as we 1s orbitals and 2s orbitals will be varying in energy. Lot of variations will be there, and as we have told in the rules that the orbitals which will vary mostly in energy in the orbitals will not take part in the bond, this covalent bond formation. It will not form the hybrid orbitals. Okay, so 1s I am not writing, I am starting from 2s. So in the ground state of beryllium, if you see, this is 1s to 2s2, right? So we got in this case, and we know that this is a stable molecule BeCl2. So we need two hybrid orbitals, of course. For beryllium, the central element, to undergo a covalent bond formation with two chlorine atoms, as we can see in the molecular formula, okay, we need two hybrid orbitals. So that is not possible in the ground state we are seeing. So that goes in the, for the excited state, what happens, one of them jumps into the p orbital. So this is the case now. Okay, so this is S and this is P, as you know, and this is px. Okay, as we have shown it in the diagram also. Now this go for hybridization, forming two similar type of atomic orbitals. This hybrid orbitals will be formed in this way. Suppose this is for beryllium. Okay, the smaller lobes on this sides. This is my beryllium, and it will go with the covalent bond formation with a chlorine atom's p orbital, pure atomic orbital. This is pure atomic orbital. Okay, for the central element only the hybrid orbital concept is there. This is pure p orbital of chlorine, one of the chlorine atom, and this side also another chlorine atom will come into play. This is also the same. Okay, so do two Cl atoms on two sides, and this is the case. And if you talk about the bond angle goes in this way. This is 180 degree to each other. Okay, this angle becomes 180 degree. This is beryllium and this is chlorine. Okay, so this is the case. Now we go for sp2 hybridization. So from the name, what you can get is that one of the s orbitals and two of the p orbitals are involved in the hybrid bond formations. Okay, so I have taken one S. You can show here X, Y and Z in the axes, which I have not shown here. Okay. Next come our two p orbitals, which will be of course px first, and then you take py. So arrangement, when these three orbitals are mixing with each other and they are forming three separate hybrid orbitals of the same energy. Okay. Now this goes in this way. This orients in such a way that the repulsions between the electron pairs are less, as we have seen in the valence bond theory, and thus this is the representation. This is how it is oriented. So this is the first lobe we are getting, this is the second lobe we are getting, and this is the third lobe we are getting. Okay, so we got three sp2 hybrid orbitals. As I told you that the number of pure atomic orbitals which are undergoing in the hybridization process, here we can see 1s and 2p, thus 3 pure atomic orbitals are going for hybridization bond process, and thus how many of sp2 hybrid orbitals will be formed? 3 of them. So this is the 3 hybrid orbitals, sp2 hybrid orbitals, which are formed. Now when we see an example, it will be more clear to you. BF3 molecule B, that is boron, in the ground state will have a configuration. So again I am not writing 1s. Okay, 2s, 2 as you can see, and 2p1. Now this is you need 3 atomic orbitals, right? So for that you don't have 3 atomic orbitals over here for the covalent bond formation, which will form the hybrid orbitals suitable for making covalent bond formation with the other atoms. So in that case, we take the excited state help, and this electron jumps from here to there. So 1 electron left, here 2 electrons left. So how many you got? 3. So 1s and 2p orbitals are involved in this bond formation, and thus when you write it, how will we write it? Suppose this is for the beryllium purpose, boron, sorry, this is boron. Boron's hybrid orbitals have formed this orientation, and next comes our F pure atomic orbitals. So here one F pure atomic orbital, here one F pure atomic orbitals, and here one F pure atomic orbitals, and this is my boron. Okay, so this is how it is formed, and we know the bond angle is going to be 120 degree. Okay, next we go for the bond formations, where we will see, okay, sp3 hybridization. We start with S, and 3 of the p orbitals, that is px, py and pz, are involved in the bond formation. Okay, now when these 4 atomic orbitals are mixing with each other, there are formation of 4 sp3 hybrid orbitals, which you are seeing in the picture, the orientations of those. Okay, is towards the regular tetrahedron. As we know, if the central element is not containing any lone pair of electrons. So regular tetrahedron geometry, that is, the angle between them will be 109 degree 28 minute. Okay. Now CH4 molecule. For CH4 molecule, when we discuss, carbon in the ground state will have 2s2 and 2p2 configuration. This configuration. Now it needs to form hybrid orbitals so that it goes for the bond formation, covalent bond formation with 4 hydrogen atoms. Now how can it go? It requires 4 hybrid orbitals. That is not possible from the ground state. From the excited state we need to go, and from the excited state what happens? One of the electron jumps over here and does what we get this way. Okay, so we are seeing that 1s and 3p orbitals are involved. So if you draw the orbitals, you can also draw it in this way. After the mixing has been taken place, we have sp3, sp3, sp3 and sp3. 4 such sp3 orbitals together now we have. Okay, which are shown here in the geometry. Now this will go for a bond formation with the hydrogens. So if I draw it, I will try to draw this here with the smaller lobes over here. Okay, and with 4 hydrogen atoms is going for the bond formation. Okay, this is for the 4 hydrogen atoms. Now let us go for sp3 d configuration, where of course 1d orbital is coming. 3dz square. First of all, this orbital is going to come because we have 5 d orbitals, we know. Okay, out of that 3dz square will come because of this orientation lies to along the axis. That's why this comes into play rather than the dx, y, yz and zx. Okay, and the diagram of d orbitals is not that much of difficulty. Okay, you can just practice it. It's very easy when you draw the axes. I'll show you in the next one also. You'll get the concept that of course 3d z square is easier here. You can see that. Anyways, all these 5 pure atomic orbitals are mixing with each other to form how many? 5. Okay, sp3d hybrid orbitals. Now you see the configuration, how it is, how the geometry is. All of them are what? Hybrid orbitals, sp3d hybrid orbitals. So the bond angle over here, you can see it is 120 degree and this is 90 degree. Okay, 3 of them will have an angle of 120 degree and 2 of them will have a bond angle of 90 degree with the next adjacent ones. Okay, and the next one, let me check it. Okay, now this is for sp3d2 configuration, where of course 1s, 3p orbitals and 2d orbitals are coming into play. Of course 3z square, so I told you, and the other d orbital which is along the axis is 3dx square minus y square. Can you see the diagram is so easy? Okay, x, y, z axis I have drawn, and along the x-axis, the lobe is along the x-axis and the lobe here is along the y-axis. That's it. Okay, all of these 6 will be mixing with each other to form in this way. The orientation will be in this way. Okay. Now I'll say is that whenever you have to draw, suppose you have to draw dxy or such cases, take x and xy. Okay, in the case of dxy, the lobes will be between the x and y axes. I have told you the image also. I have shown you in the image also. That you can check, and then the previous day I told you for our homework also. You didn't do it. So check for that. Okay. Now for sp3d2 configuration, we can take an example of SF6 molecule. SF6 molecule, in the similar way, you have to see whether in the ground state it is able to form the hybrid orbitals or not. Then you can go for the excited state. You can go for the excited state and show that yes, there's now a possibility of hybrid orbitals forming, and then you can draw this in the orientation. All the 6, of course, sp3d2 hybrid orbitals you will get, and that you can just show it with the fluorine's pure atomic orbital configuration, the overlapping of, in the case of formation of a covalent bond. Okay, so that you can show it to me. This is what you are going to do it now. Now, next, I told you that I'll tell you the geometry of the molecules containing a lone pair of electrons. That I'm going to tell NH3 molecule. See, in the ground state, of course, what happens in the case of NH3, this is what it happens, okay. 1s2, 2s2 and 2p3 is the configuration. Now what happens is that in this case, in the ground state itself, the s and the 3p orbitals will be forming 4 sp3 hybrid orbitals, out of which we know, when we draw this N, H3, suppose 4 sp3 hybrid orbitals, let me draw it first. Okay, this is for nitrogen. Central element is going for hybrid bond formation, okay, hybrid orbital formations. To make sure that it can go for the covalent bond formation with the other atomic orbitals of the other atoms. Now, in this case, out of this 4 sp3 hybrid orbitals, 3 are going for bond formation with hydrogen. And the other one, which you can see, the paired one, this is containing the lone pair of electrons. So one of them is containing the sp3, one of the sp3 hybrid orbitals is containing the paired electrons, is actually the one which is containing the lone pair of electrons here. Okay, this is how it happens. And you know, because of that, the distorted geometry is, the angle changes from 109 degree to 107 degree. So this is what the case. You can also show with the water formation, water molecule formation. Similar way, you just check it out in the ground state itself. It will undergo hybrid orbital formation, or it will undergo hybridization, because you know, that is the way it can undergo, because it also needs to have the orbitals containing the paired electrons. Okay, that is this type of paired electrons. So the lone pair of electrons will stay in those two, maybe here in the case of water it will maybe 2 such hybrid orbitals. Okay, so let me go for the next one, which is a very interesting one, that is the number of orbitals which is involved in the hybridization can be determined by applying formula. Suppose, how did I understand that NH3 will be going for the hybridization process in the ground state itself, or water will go in the ground state itself? How do we know it? There's a formula for that. Just check it out. H equals to plus half in brackets V plus M minus C plus A. That is, H is the number of orbitals involved in the hybridization, and V is the number of valence electrons of the central atom. M, capital M, is the number of monovalent atoms linked with the central atom. C is the charge of the cation. A is the charge of the anion, in case those are ionic ones. So let us try for few ones. That is, the first one is CO2 molecules. Valence electrons here is 4. Okay. Now see, the next one you have to check is M. M is the number of monovalent atoms. Monovalent word is there. Okay, so I know you'll be knowing that oxygen is not a monovalent atom. Oxygen is not a monovalent atom, it's a divalent one. So we'll take 0 for this. M equals to 0 here. C equals to 0 because it's not a cation, and A equals to 0 because it's not an anion as well. So now when we do it, half, we got just 4, right? So cancellation will give me what? 2, right? So you start from S and then P. So this 2 hybrid orbitals you have. So this is undergoing, CO2 will be the central element will be undergoing sp hybridization. Now let us check for NH4 plus. Okay, let us check for NH4 plus. So how does it goes? Like, valence electrons will be, for nitrogen it will be 5. Okay, and M equals to monovalent atoms. Here we can see 4 of them are there, 4. C, it is a charge containing positive 1 charge, so it is 1, and A equals to 0, of course. Now half of this is 5 plus 4 plus 1 from the formula, and thus we get 4. So starting from S, it is sp3. Thus this is the number 4 you are getting, right? From S, if you start S orbital 1, number 1, and other 3 p orbitals, so total 4. So the hybridization of nitrogen in case of NH4 plus is sp3. Okay. Now let us check for CO3 2 minus, or you can check for PCl 6 minus. Let us check for CO3 2 minus. V is equals to 4 here. M, monovalent atoms are not there, 0, and C equals to 0, A is equals to minus 2 over here. Okay, so hybridization comes as half 4 plus 2, that is 6. Okay, now if it is 6, so cancellation, that will again give me 3. So this is sp2 hybridization. 3 hybrid orbitals, that means starting from sp2. So 1s and 2p orbitals. So 3 in total. So 3s. So the hybridization of carbon in case of carbonate anion is sp2 hybrid or hybridization. Do it for PCl6 as well. I have given you 2-3 things to do here in the video. First show me that and then we'll discuss. Okay.